Right, okay, let's get started. So for review of last time, right? So last time we covered power electronics and basically the half-wave rectifier. So from last time, we covered was a half-wave rectifier. So if you have a source, we can either put in a diode or we can put in SCR. Okay, so if the source is a sinusoidal source, then the output is entirely positive. And by changing the triggering angle on the SCR, we can get a different different average voltage or the root mean square voltage to show up over the load. Right, but the fundamental difficulty with this kind of approach is you lose half the wave. Right, so if you look at the low voltage, as you get half the wave, then nothing happens. You get half wave, then nothing happens. So this may not be very efficient, right? So you half of the energy or half the power doesn't come through the rectifier circuit, right? So the hope is, so we'll start this class by covering something called the full wave rectifier, and then we'll go to DC-DC converters. So the idea of the full wave rectifier is quite simple. It's basically saying that if the source is something like this, then at the load, what we want is we just want everything to be positive. Right? So we want to have both the positive and negative part of the rectifier of the source show up as a load. Right? So this is called a full wave because you're capturing all the AC wave. You're capturing all the AC wave compared to half-wave rectifiers where you're only capturing the positive part. So making a full wave rectifier is relatively straightforward. It's relatively straightforward. And the way you do it is basically do this sort of bridge design. Okay, so this is the 4-diode full wave rectifier. So this is sometimes also called a bridge. And by using 4 diodes, we can create 2 different paths from the source to the load. And this way we can capture the entire wave instead only of half it. And then the idea is quite simple. The idea is quite simple. It's basically if you look at the source, the only pairs of the diode can be on at the same time. Okay, so remember, these diodes, we're going to assume the diodes start conducting once its voltage is sort of forward biases, its forward bias voltage is greater than 0. So if you have a source like this, then basically for this period, for the period from A to B, right? During this half of the wave, we have VA greater than VB. So in this case, D3 and D4 are off, right? They are not conducting. And D1 and D2 are off. So you follow this path. This is positive, so this diode is conducting. We'll come here. This diode D3 acts like an open circuit. So we'll go through the load, and this is the current flow. The current flows this way. So flow through D1 and D2, D3 and D4 are open circuits. Then the voltage is higher at point C than point D. So we still capture this part of the wave. Right? We still capture this part of the wave. So both of them are on. Then if you look at whenever the voltage is negative, right? Whenever the voltage is negative, a similar thing happens. this is the period of interest for us. So here, D1, D2 are off, so they act like open circuits. And D3, D4 are on, they're conducting. So if you follow the path, then the current has to go this way, comes down here, and goes up back here. So again, the voltage across the load is still positive, right? Still as the voltage is higher at point C than point D. So we capture the other half of the wave. So for this part of the wave, we still reflect upwards. We still reflect upwards and capture it. So here we capture both the positive part. So this comes from, right? So this green part we have from before. And then this red part, the different set of diodes conduct. And then we also get a positive voltage across our load. Okay? So this is how we achieve a full wave rectifier, right? We're not losing any of the voltages. We don't lose any of the voltages from before. Any questions about this? Right, okay, so this is sort of very straightforward circuit to build. You build this diode bridge, right? Or thing with 4 diodes. The observation is you cannot build this with less number of diodes. So for half wave, you need only 1 diode, but for full wave, you need 4 diodes. So that's just the way the circuit works out. You can try taking out any of these diodes. Then the circuit wouldn't necessarily work. So the requirement is you need 4 diodes to build a full wave rectifier. But the operation is quite simple. It's just basically comparing, when the voltage is positive versus when the voltage is negative, and we'll reflect the negative part up. We'll reflect this part up. So we can compute both the average and the RMS voltage across the load, right? So similar to the half wave case, we can now compute the full wave average voltage across the load. So the average for the full wave rectifier, now we have to integrate, right? We integrate over the entire period. There are 2 pi, let's say V max sine omega t, d omega t. So this, we get V max, 2 V max over pi. So if we do the calculation, we get the V max scaled by 2 over pi. All right, then we can also compute the RMS voltage across this, right? We can compute RMS voltage. So RMS voltage, so VRMS. Just by looking at this figure, what's the RMS voltage? Without doing any integrals. We know this number, we don't have to do integral. What's the root mean square? What's the RMS voltage of the full wave rectifier?
V max divided by root.
Right, V max or square root 2, right? Nothing changes. Nothing changes from when you have an AC wave versus when you have a full wave rectifier, right? Remember
I have a question about that. So on our homework, so last week, I think it was problem 3 and 4. One of them was just a sine wave and the other one had the plus 0.05. So anytime we have an additional, I think it's a DC signal attached to that sine wave, you can't just say that, right? Because like on the homework last week, the answers for problem 3 and 4 were virtually identical. I mean, I think they were pretty much the same response. However, there's a one on this week's assignment where I think there's like a 3-volt difference. So what's kind of the rule of thumb on that?
So this V max over root 2 works for AC wave with 0 offset. Right? So that's when we did the integral, we integrate over a sine squared. right? So that's how we got this equation. So if you have a DC offset, now of course a DC offset will change the answer. Because if you square a sine plus a DC offset, you square that, there'll be a cross term that comes out. Right? So there'll be a cross term, it'll be the DC offset squared. So the DC, of course, then the answer changes depending on what the DC offset is. Whereas in this case, right? So if you square both of the signals, you get exactly the same thing. Right? A sine squared is the same as the absolute value of sine squared. Right? So this is exactly, so if you look at this function, this is Vmax sine omega t, right? This is Vmax absolute value of sine omega t. So when you square this, right? So when you square, so the observation is Vmax sine omega t squared is exactly the same as Vmax absolute value of sine omega t squared, because the square doesn't matter for the absolute value. So we can use, the absolute value doesn't matter when you square it. So we can use Vmax over root 2 as the answer we got before. When you have a DC offset, that is different. Then you have to square it actually.
So is there a shortcut way to do that without having to do the full integral? Or is that the only way to do it if you have a DC offset?
Oh, we have a DC offset is quite simple, right? So you don't need to do the integral. So if we want to look at that as a side. So let's say this is sine omega t plus some DC offset, let's say A, right? Square this. This is sine squared omega t plus A sine 2A sine omega t plus A squared, right? And when the integral, we're going to take a square root, right? Then, but this thing integrates out, so this is a square root of 1 over 2 pi sine squared omega t d omega t 0 to 2 pi. Right, so this we know how to calculate, right? This we know. This comes from from the RMS calculation we did before. What is this integral then? What is this integral? We have a sine integrating over a period.
Averages to 0.
0, right? So then we have A squared. So this is quite simple. This we know. The first term we know, we computed before. Right? When we did the RMS computation, we explicitly integrate this. Or we, basically this is a square of the RMS. And then you just add that to A squared and then take a square root.
Awesome. Thank you, sir.
Yeah, so it's not, right? So whenever you get a question in this class, there is no hard integrals we have in this class. Right? It's either integrating a constant, maybe a linear function, or a sinusoid that integrates out to there. Right? So integrals are not hard. There's no tricky integrals to do. Right? So if we have a tricky integral, then you know the answer. Right? You know the answer. You don't have to do it on your own. Okay? But in this case, right? So the RMS doesn't change once you pass it through a four-way rectifier. So the same RMS value as before. Okay. Any other questions for this? All right, so here again, we're capturing all the wave, right? So if we want to change how much, what's the average voltage or the RMS voltage, exactly as before, as you now use a SCR, right? So instead of using for diodes, you change 2 of them to be SCRs. So you swap 2 of them to be SCRs. Then, well, the power flow doesn't change all that much. Still, you have both S1 and D1 are on. if they're on at the same time, you get some positive voltage across the load. The only difference is this now has a triggering angle. This has. So it doesn't immediately turn up once the voltage is greater than 0. So you need to trigger this. But once you trigger it, it operates exactly as before. Similarly, you have for the red path, it's similar. You trigger S2, you trigger the second SCR, you still have positive, voltage across the load. So here is depending on when you trigger it, you cut off, part of the wave. You only start after the angle alpha. Any questions about this? Okay, so then practically, what do you need to be careful about when you're designing the circuit? It's a bit, this are some, if you have 4 diodes, not much can go wrong. But have this circuit, what are the potential problems you may have?
The like breakdown voltage on the diode.
No, not really. So that's always a concern, but normally we don't run into that.
Okay.
Be careful when picking your alpha.
So here is one is, don't trigger them both at the same time. Right, so don't trigger both S1, S3. Both, right? Don't trigger these diodes at the same time. So let me actually change this notation. S2, D2, D1, maybe more consistent. Right. So don't trigger the blue and the red SCR at the same time. And make sure your program is correct. These two are not on at the same time. They're on at the same time. You create a short, and that's not good. Right. So this can happen. Actually, so when you do programming, this is one of the bugs that can happen. So you need to make sure your logic is correct, right? Your timing is correct. Make sure one is off, the other one on. Turn them on and off like that. Okay, so this is our. This is still a pretty simple circuit. Right? You have one source, you put 2 SCRs, 2 diodes around it, then you get a controlled full wave rectifier. Right? So you can control the average voltage and the root mean square voltage. So here I'm not going to, right? So average voltage is just another integral. So again, not very complicated. So here we get dependent triggering angle alpha. So the dependence is 1 plus cosine alpha. So this is our dependence. Then the root mean square voltage is a bit more complicated, but still it's an integral we can do. So the RMS voltage, this is V max squared over 2 pi, 0 to 2 pi, or let's do this integral. So here, when we integrate this, so if you look at the voltage, it'd be something like this. This is on at the angle alpha. And then this is again on at the angle alpha. So our integral, we can integrate is twice of the 2 times the square of the area under the. So it's 2 times the integral you will get when you integrate one of the pieces. So what we have is V max squared over 2 pi times 2 times integral of alpha 2 pi sine omega t squared d omega t. Then if you integrate this, we get something like V max or square root 2 square root of 1 minus alpha over pi plus sine 2 alpha over 2 pi. Okay, so this thing scales as a function, as a somewhat complicated function of alpha. But once you do the integral, we just get this equation.
Quick question.
Yeah.
Is that the parenthesis at the front?
Oh yeah, so this is whole thing. Whole thing is under the square root.
Okay, thank you.
So we get the whole thing under the square root. Then our power is still VRMS squared over R. And if you take the square, you do some manipulation of the terms, this is what you get. So for us, for you guys, you just need to know where to find these equations. All right, so one thing to be careful is here, all this equation are given in terms of Vmax. Right, so here, the thing to pay attention to is these are Vmax. When you're doing a question, you may well have the question giving you the information in terms of the RMS voltage of the source. So if you're given information like that, you need to be able to convert it. So when you're doing a question, the question will typically say, you have a source with a voltage, let's say of 110 volts. That will be actually the RMS voltage of the source. So when you want to use these equations, you need to be careful whether these equations has Vmax in them or these equations have the RMS voltage of the source in them. Okay. So that's just something to be to pay attention to. Okay. So this is a table summarizing this. Again, things to remember is here we're just giving you the information in terms of Vmax of the source. Okay, so here, max, this is the Vmax of the source. Any questions about this? Okay, good. So if you look at beside the sort of from the two columns, we'll recognize that. So what is VRMS? Let's say we pick the same alpha, right? So okay, so for diodes, put alpha equal to 0. Right? So if you have a diode, you can, as alpha are diodes, you can put alpha equal to 0. You recover the equation you want when you have a diode. So here, if you look at it, VRMS of a half wave rectifier is the square root 2, right? Differs from VRMS of a full wave by square root of 2. And the power differs by a factor of 2. Okay, so that's something to also be useful to remember. Okay, so if you look at the power from both sides, there's a factor of 2. Whereas you look at the RMS voltage from both sides, there's a factor of square root of 2 difference. Okay, so this is sort of the table you can look up and then to do we can do our problems. We can solve our problems from this table. Right. So a lot of problems for a full wave half wave rectifiers are fairly simple. It just requires to read this table, and we don't, there's not that much going on. If you're given a lot of information, you just have to, find the power, for example. All it requires is reading this table. So next, we'll do an example that's a little bit more interesting. Okay, so let's do an example that's a little bit more interesting. So let's say we have a full wave AC to DC converter, and we connect to a load of 5 ohms. The AC voltage, right? So AC source has 110 RMS. And we require the RMS voltage across the load to be 90 volts. And we want to compute the triggering angle alpha and the load power. All right, so for this type of question, what we want to do is, so of course, you write out you go to the table and look for the equation, right? So this is the full wave. So we're going to use this equation here. We're going to use the second equation on the right column. So that equation tells us VRMS this is Vmax over square root 2. So this is our equation we can read off from that table. Right, and we can substitute the given information we have. So we want 90. We want the load RMS voltage to be 90. This is the source RMS voltage. So this is 110 angle of 1 minus alpha pi plus sine 2 alpha over 2 pi. Okay, so any questions up to now? Okay, so we need to solve this equation, right? We need to solve for alpha. So one way to solve for alpha is to square both. Divide this over, square it, and we get 1 minus alpha plus pi sine 2 alpha 2 pi. Or if you manipulate this around a little bit, if you manipulate it around, we get alpha equals to 331 pi plus sine 2 alpha over 2. Right, so we want to find the alpha where this equation is satisfied. So at this point, we have, you have many options. One option is, right, since we can use computers in this class, or you can use graphing calculators, you can use whatever you want. You can just plug into a computer and solve it. You can graph it. You can plug into the computer and solve it. You can use some nonlinear solver if you know how to use them. Whatever those tools are fair. So when you do your homework or when you do your exams, you just have to say, I got the equation to be in this form. Then I solve it, by graphing or using Python or however you did it. Okay. But then suppose you don't have access to those tools, right? Suppose you don't have access to those tools. Any of you have an idea how to solve this? Right, so the easiest way is just to tell this to a computer, and any software today will solve this for you. But suppose we don't have that. I suppose I really want to solve this equation, and all you can do is say a calculator that can do sines, that kind of trigonometry. How will you go about solving this? Any ideas? For example, if this was a more traditional sort of, in-person class, so when you do your midterm, you don't have access to a laptop. You have to solve this somehow. Any of you have seen this type of equations before? Okay, so this is a so-called fixed point equation. And one way to solve this equation is through the following iteration. So here, alpha is a fixed point. What this means is alpha shows up on the left, also as a function on the right. Okay, so what you hope to do is the following. As we pick alpha 0 some value. We pick alpha 0 to be some value. Then we repeatedly calculate alpha k plus 1. So we have alpha 0. We're going to plug it in. I'm going to calculate the next value for alpha over 2 pi. We're going to repeatedly plug in alpha k. And the hope is we're going to hope that the values are as k goes large, these two will converge to a fixed point, will converge to some fixed alpha, right? Then we know that we have solved this equation. Right? So this is interpretation of basically what the equation is saying is you're putting alpha to the right-hand side, you get alpha back at the left-hand side. And you can repeat this procedure to solve for alpha. So if you use this, if you actually use this, what we can do is, again, remember our equation, the iteration we want is alpha k plus 1, 331 pi plus sine 2 alpha k over 2. So we're going to pick alpha 0 equals pi over 4. Right, so pi over 4 doesn't solve this equation, but we can still pick it. Then if you substitute alpha x to the pi over 4 into the right-hand side, you get alpha 1 as 1.54. Keep substituting that into the right-hand side, 1.07. Alpha 4, this is 1.15. You keep doing this, and eventually you get this thing to converge alpha equals to 1.3. Right, so the values will oscillate, but they'll get closer and closer to each other, and eventually this will sort of converge to a single number, and then you can read that out to be the alpha. Any questions about this?
I'm still confused about it.
Okay, so the
it's-
procedure clear, right? So you're picking alpha equals 0 equal to pi over 4. You put it into the right-hand side. So you do this computation.
Can you pick anything else beside pi over 4?
Oh yeah, you can pick equal to 0. You can pick equal to 0, right? So this gives you this number. Then you substitute alpha 1 equal to this number, 2 times 1.54 over 2, and you keep going. This is a fixed point iteration.
So you can
So
pick
here-
any that's give you the value of 0.
No. You can pick alpha 0 to be any, most times anything you want. So you can pick it to be pi over 3. You can pick it to be 0.1. You can pick it to be some number.
Okay.
Right. So you have some freedom to pick.
So how many iterations does that take till you get to 1.3?
If this converges, will converge very fast. This will converge exponentially quickly if it converges. So if we fixed point, so this is called a fixed point algorithm. And fixed point equations, if they converge pretty quickly. They may not converge, but if they do, they'll converge quickly. And if you see a question like this, we'll pick a problem such that this will converge. Another question about this procedure? Right, so if you know how to solve this type of equations without using this fixed point procedure, or no, you just want to graph it and read it out, that's fine. If you don't want to do that, you want to do the fixed point, you can do the fixed point. So however you want to solve this equation, it's fine. Okay. All right, okay, so this is a way to solve this type of equations, and this happens this is actually quite close to what will happen in practice. is you set what the low RMS voltage you want across the load is, and then you need to compute this alpha, right? So in your control software, you need to compute the alpha, and then that's when you set your trigger. So this is solved pretty often. So different load have different RMS requirements, and the alpha needs to be adapted depending on what the RMS requirement is. And here is an example is we don't have a closed form formula for alpha. Right? So given 90 volts as the output RMS voltage, it's not, we don't have a direct formula I can plug into to find alpha, but you can do a few iterations and find the triggering angle. Okay, so it's not very difficult, but just that we don't have a formula. Right. Then also, if we want here, we are asked to compute the low power, and the low power is easy to compute because power is RMS squared over R. This is 90 squared over 5. This is 8.1. It's not right. Did I do this correctly? So you get 1.6 kilowatt. Okay, any question about this problem? So you see this type of problems in the homework, and you see this type of problems in the exams. Just because this is just a common way of how to set alpha. So normally, as you don't have an alpha in mind. Alpha is determined by what the load wants.
I have a question.
Mhm.
So for the alpha value, when you do like the designs and stuff like that, like you said, like if we have like different like like sine wave, and you have to get like really accurate timings for alpha, but in this step, like 6 step, it's take a really like a lot of step to get like the alpha value. Is that the accurate value enough for the timings of alpha?
Oh, so this is actually not that many steps. I mean, you ask your computer to do this, you can, any processor will do this in no time at all. And here I was lazy. I just kept a few decimal places, but you can keep many decimal places if you want.
Would MATLAB able to do this one?
Oh yeah. MATLAB will do this easily. Okay, MATLAB can go to whatever the floating point is, can go to probably 15 decimal places if you want. Right, so it only matters up to it, right? So you don't need that many decimal places in practice, right? If you're measuring angle in terms of degrees, 2 decimal places of degrees is more than enough for us. All right, so here, again, it's good to notice that this is not harder to do compared to a equation, right? So, sometimes we think if we have a closed form equation, that's easier to do. Not always the case. This, you can, for a computer or for a microcontroller, solving this is as same effort as implementing some equation you have. Any other questions about this? Okay, so you see some type of this questions in the homework this week. Okay, so again, if you don't, right, if you don't want to use the software, you don't want to directly call a solver, then you can use this sort of fixed point iteration method. This is very robust and will converge pretty quickly. It doesn't take that many. All right. So then this is our AC to DC converter, right? Our most flexible AC to DC converter is a full wave rectifier, because it gets both part of the sine wave, and by changing alpha, you can change your output voltage. And so that's the most flexible. So one thing to note, the important thing to notice, the way we draw a full wave rectifier, what we get is something like this, right? Okay, if your device consumes DC power, it would not be happy if your voltage looks like this. Okay, this is not a very nice DC voltage. What you really want is a very flat voltage. And you achieve this through filtering. So you have to filter. But so the normal circuit design is, well, here you have is you basically have a LC filter. So this is some inductor and some capacitor like this. And then you have a load. And then you can keep the average load, right? You can keep the trace on the load fairly constant. You can keep this fairly constant. All right, so we do not cover filtering at all. That doesn't mean filtering is not important. Filtering is often as important as your filtering is a very important part of your converter design. Right, so in modern converter design, more than half of the effort comes down to how you filter and how you package these things. In this class, we're not going to deal with this. We're going to learn the very basics. How do you flip the wave, right? How do you make sure it's all positive? And then the filtering, we assume, is taken care of. But really, if you become a power electronics designer, a lot of your time is spent on filtering, designing the filter elements.
So they use a bandpass or something completely different?
It's not exactly a band pass because you don't want to block off power, right? So it's not really a band pass. It's more like you want to, so you really want to store and release energy in such a way that your output is a constant voltage. So one way you can think of is if you're going to filter, if you have a really big capacitor, that will help. Right? One simple way to filter is put a really big capacitor. Then if the capacitor is really big, then your output looks roughly constant because capacitor can hold the voltage. So of course, in practice, we cannot just add in large capacitors. We don't have enough space to do that. We need to be clever in the filtering design. Okay, so this is actually a lot of power electronics design is how do you do this? But how do you deal with the passive elements? How do you make them small, make them efficient, make sure you don't lose power by switching too quickly through a capacitor? All those kind of issue comes in, which we are not going to talk about, but definitely something to keep in mind, right? to know, right? Why sort of power electronics design is not trivial. You may look at the full rectifier and say, oh yeah, it's easy to design a converter, it's easy to design this kind of rectifier, but really the trick comes down to filtering and packaging and getting rid of heat and things like that. All right, so the same story happens for DC to DC converter. Again, we're just going to make sure the average come out correctly. We're not going to worry about how do you make the waveform look smooth and look nice. Right? But still, that's a very important part of the converter. It's just that for this class, we don't have enough time to cover it. We don't have really enough time to cover sort of sizing. besides the basic, besides some very basic things. Right, so that was AC to DC. Now let's look at DC to DC converters. Okay, let's look at DC to DC. So DC to DC converters, there are 3 types of DC to DC converters. So for short form, we can have a converter, we have V, let's say V in and the V out. So the first type of converter we can have is a step down, or more often than not, this is called a buck converter. So this is when V out is less than V in. For example, this is commonly seen in the electric vehicle, where the motor drive may require different voltage level than the onboard for computing electronics. So you may need to step down the voltage. Then what we have is a step up. This is called a boost converter. Right, so it's exactly what the name says. Will increase the voltage level, right? So this is VL larger than VE. Can you think of another converter? There's 3 actually. So there are definitely applications where we need to rise or lower the output voltage compared to the input voltage. Are there other situations? Are there other things we want?
Like a buffer.
Not really a buffer. So we don't buffer it. We just so we're going to look at the output voltage. So we could, let's say you have some input voltage. We may want the output voltage to be higher. That's where input voltage is 5 volts. We may want the output to be 10 volt. We may want the output voltage to be, we may want it to be 2.5 volts. What else can we want it to be?
What you just said, negative, you want to invert it?
Right, you want to invert it, right? So what else? Also, you may want actually to reverse the polarity of the voltage. So this is called a, right? So again, engineers are not very inventive with names. This is called a buck boost converter. Not sure why they could not come up with a good name, but this is called a buck boost converter. This is V in. This is V out is minus some factor times V. So reverse the polarity. So when do you want to reverse this? For what application do you want to reverse the plus minus terminal on the voltage?
Motors to drive it backwards and forward.
Sure, that's one way you can think about. But that you can do a lot of times through the gear. Think of electronics applications. Electronic application where you want to reverse the polarity. So a lot of times we want to reverse the polarity. So there's easy commercial applications. As nowadays, let's say if you have an iPhone or any sort of smartphones, it doesn't matter which way you plug the charger into it. Okay, right? So nowadays when you have a phone, let's say you have a charging cable. Right, so this is my iPhone charging cable. You can flip it around, you can still charge. It doesn't matter which way you plug it in. So most of you probably don't remember this, but when iPhone first came out with this charger, it was actually a big deal. You're not limited to a single way to plug it in. And that's basically, you have a way to reverse polarity. Right? So you can both negative and positive voltage level will work. Right? So this is sort of the 3 types you may want, depending on different applications. Right? So, and in different applications, you see different types. So integrated circuits, you may see more buck. Some other applications, you may see sort of more boost conversion. Right, so now is a good time. So let's take our break now. So let's break until 3:33. Then we'll run through the 3 types of DC to DC converters. Okay, so let's resume in 3:33. Okay, let's get started again. All right, so we're gonna start with the first converter, the buck converter. And this is a really simple converter. Okay, so for us, buck converters are really simple. All it is a source in series with a switch with a load. Okay, so if you think of this as a switch, then our circuit is this. This is all our circuit is. Right? And then all we're doing is the switch is a bipolar transistor, so it's controlled by the current pulse. So by the base current. So if you send in some base current, you can turn the switch on, and then you'll see some current at the load. Then then you see some current at the load. So if you then stop sending current at the base, and the switch turns off, then the switch turns on again. So this is really a simple switch. And then obviously you get less average voltage at the output because the source voltage is really constant, right? Where the low voltage is the source voltage when the switch is on and 0 when the switch is off. So depending on how long the switch stays on, you have you have less average voltage compared to the source voltage. Okay, then so again, the calculation is quite simple, right? Calculation is quite simple. So the average voltage, right? So what is the average voltage then? Well, if I have a period of tau, and out of that, you have T on, then the average voltage is simply 1 over tau, 0 to T on, Vs dt, but Vs is constant, right? So this T on over tau times Vs, and this is K times Vs, where K is T on over tau, and here K is the duty cycle. So really, this is sort of very simple equation. And we don't need the other components for our buck converter, right? Since we're not filtering, so all we're doing is we're just turning it on and off sometimes. Any questions about this buck? Really, there's not much you can say about the buck. It's more interesting for the other 2 converter types. For buck converter, this is relatively simple. Right, so let's do an example. Let's say I have a switching frequency of 5 kilohertz. I have the source voltage of 12 volts. The output average voltage is 5 volts. We want to compute what T on is. Okay, so the first step is for all those type problems is you want to compute the period, right? Most times the switching is given in terms of frequency. So we need to take 1 over f to find the period, 0.2 milliseconds. Then we know that the average voltage is T on over tau times the source. So 5 T on, 0.2 milliseconds times 12. Solve this equation, we get T on is 0.0834. milliseconds. Right, so if you keep the switch on for this amount of time, you get an average voltage of 5 volts. Any questions about this buck converter? So again, not much. For us, buck converter is super easy. Again, if you do integrated circuits, buck converter gets much more interesting. But for us, since it's really one equation, buck converter is described by one equation.
I have one question. So in the previous section that we talked about that the DC electronics wouldn't want a choppy voltage.
Right.
I guess I'm a little bit confused seeing the T-on graph up there. It looks like it's like a square wave. And how does it work? Like how do you get a steady voltage out of the buck converter?
Oh, right. So in reality, you have a filtering element. You have a capacitor after. In reality, you have a capacitor. Right, so let's just actually look a little bit without going through equations what a capacitor would do. Right. So that's a good question. Right? I'll have a very choppy wave, and definitely, no device will operate with that wave. So let's look at this circuit instead. Let's say our switch is still ideal switch, but let's say we add a capacitor to the load, right? So we still have a resistive load, but we add a capacitor. Let's look at what this voltage is now once I add a capacitor. So Vs to Vl. Right, so without capacitor, we have a choppy voltage. So with capacitor, what happens? Does anything change in the right? So during this period, okay, so if you close the switch, right? If you close the switch, then what happens?
Capacitor begins to charge.
Capacitor begins to charge, but then what's the voltage on the load?
Would it be the voltage of the capacitor?
Right, but in this case, capacitor connects to the source, right? So I'm going to close the switch, right? So I'm going to close the switch. So I have both of them parallel to the source. So you have this. Then if you open it, then what happens? What happens to the voltage on the load?
Capacitor discharges.
Right, so it goes down, right? So the voltage goes down, but cannot go to 0, right? Because it takes some time to discharge the capacitor. So this will drop, and this drops based on the RC time constant of exact value of RNC. Then goes up again, then sort of drops, right? So this is one way to filter it with a capacitor. So here is my sort of very crude drawing of what happened with a capacitor. Right? So you can compute what all these curves are. Right? So the way this works is you add the largest, you get the largest capacitor that can be added to your circuit, then you design around that. The trick is it's not always possible to find a large capacitor, or it's not always possible to add in a very large capacitor given the circuit you have. So the trick is, if you're limited in space, and the capacitor, depends on the space you have. So if you cannot have you have a super large capacitor, you solve every problem. If you cannot have a super large capacitor, you need to design around it, and that gets interesting, right? That gets very interesting. Right, and in practice, you have to worry about, what if you have noise? What if your load suddenly changes, right? So remember, you're switching. Then what if your switch is off? So you have an open circuit, but then your load suddenly changes. Then what happens to the behavior? Can you still keep the voltage within bounds? And all that needs to be considered. We'll design this we actually design the circuit. But for us, as we get the average correct, adding a capacitor really doesn't change your average, right? It's not providing anything. So it's You can think of this as for smoothing. Then you want to sort of pick the right values. You want to size them correctly, but that's a much more advanced problem than we'll handle in this class. So in this class, we'll just get it to look like this. Then we'll declare victory, and then somebody else. Or if you go on to other classes, you learn how to design the rest of the circuit. But that's a good question.
Thank you.
Yeah, so think of this class as a very introductory class, right? You don't want to just take what you learn in this class to get a job and do what you learn in this class. What you should do is this will introduce the basic concepts. Then you sort of refine the things you learn in this class to other classes that we have in the department. Right, so I teach a buck converter like this. I talk to my colleague who teaches buck converters for integrated circuits. And he always laughs at me because I say this is a buck converter. So this is the front end. This is sort of the very first part of the circuit. So let's skip this. It's sort of the same calculations again. Let's look at a more interesting circuit. Look at a more interesting circuit. This circuit actually has inductors and capacitors, and a diode, and a switch. Okay, so this is in some sense the first non-trivial circuit we'll look at. And the goal of this is a boost converter. The goal of boost converter is we want VT to be larger than VS. Right? We want the output voltage to be larger than the input voltage. And the way you do is through having a capacitor, basically a inductor and capacitor through storage elements. So if you want to raise the voltage, you need some storage to raise your voltage. Okay, so let's see how this thing works. Right, so this is non-trivial circuit. So the way to analyze this is always to think of two possible situations, right? When you have a closed switch and when you have an open switch, right? So if this switch is closed, then you don't care about the second half anymore. Right? So if we just look at the closed switch case, if the switch is closed, you have a short, right? The transistor becomes a short. So the rest of the circuit doesn't matter to us anymore. Then what happens when you have a closed switch? Right, so what happens when we have a source, DC source, in series with the inductor? Right, so we charge the inductor, right? So how this is correct, we charge the inductor. Right? So here is where we're trying to boost voltage. Right, we have add more current into the inductor. Then when the switch is open, now I have a voltage source and I have an inductor. So both of these, we're going to try to raise the voltage. I'm going to try to raise the voltage because I have voltage coming out of VS, but then this inductor is also putting out current, right? It has to discharge, putting out current, so the voltage goes up. This is our way of raising the voltage, is by putting current into the inductor and taking it out. Any questions about this? Right, so this is intuition. So we'll do more calculations, but this is intuition. As my inductor is really acting as a storage device. Okay, so next, let's look at exactly how the current charging works. Right, so we're charging the inductor, we're putting current into it. Let's look at how exactly it works. Right. So now let's look at a case when it's on. So let's draw this. So this is time, the x-axis is time. This is current, this is current. So let's say this is my T on, this is my T off, this is my T T on. So what does it look like when you're on, when the switch is on, when you're charging inductor? How does the current behave as a function of time? Right, so if I have a DC source, right, have a battery, inductor, I connect it back. Then if I measure current, what does the current look like? Any ideas?
Does the current in the overall circuit decrease over time?
Can it decrease over time? Does it decrease or increase over time? I guess that will be my question. Right, so let's look at the inductor equation. Right, so L di dt is equal to V, right? The voltage across the inductor. So when it's T on, then the voltage is just Vs. Then what happens to the current? If the derivative of the current is a constant, then what does the current do? When it's on, then yeah.
Increase over time?
Right, increase over time, right? It's linear. Right, so because the derivative is some positive Vs, so it's an increasing line, right? So it has to increase. So let's say this is what happens, right? Starts at some value and then has a change of delta I. Right, so this change is delta I, right? So increase by delta I. Now if I turn it off, what must happen? Can it increase more or would it decrease? What must happen just from a stability point of view?
Decrease.
Has to decrease, right? So this is circuit, right? I cannot have net current in the inductor. I don't want to blow the inductor up, right? So I cannot have a, I cannot keep storing current into the inductor. So at this time, current must decrease, right? Current must decrease and must come back to the same level, basically. Has to decrease like this. And when it's on again, it increases again, then it decreases again. So this is how the current looks, right? So when the current decreases, that means the voltage across the inductor is negative, and that means the alpha voltage, the low voltage, is higher than the source voltage. Right? So this is the basic operating principle. You put in current, but I cannot keep putting in current into the inductor. This circuit, right? You cannot have a net increase in current in the inductor. So it will charge, discharge, but when discharges, the voltage at the load has to be higher. So that's how you step up the voltage, because the voltage at the load is higher than the voltage you have at the source. Any question about this intuition before we get started the equations working? Okay, so from this intuition, what we have is, right, so you have two circuits. Then the net current is 0, right? We cannot always push current into the inductor. So delta I, the increase at T on is equal to the decrease at T off, right? So the increase during T on, this is equal to the decrease during T off, right? So this is our basic conservation law. This is our conservation law. Then from this conservation law, we can pretty easily compute what the voltage will be, right? Because we have a simple voltage equation, we have a simple equation relating the voltage to the current. Right? So recall that voltage voltage is L di dt. This is roughly equal to L if we assume the currents are delta I over delta T. Right? So we know delta I is the same from both sides. And from this, we can compute what the voltage is. We can easily compute what the voltage is. So let's do this calculation. So when the current, right, when the switch is on, we have the voltage across, right, we have the source voltage is equal to L di on dt. This is L E times delta I on over delta T, or over T on. Okay, over T on. Any questions about this? About this calculation? So we can rearrange this. We get delta I on, or delta I on, that's equal to Vs T on over L. This is how much we charge, how much current we're charging. Then we're discharging, and here we're going to ignore the diode and the capacitor for now. Okay, let's just say we're discharging, and what happens is, what we must have is my source voltage, right? My source voltage has to be higher than my load voltage has to be higher than the source voltage. Right? So Vt minus Vs, right? This has to equal the amount of discharge I have during T off. So here, my voltage across the inductor leads to a current discharge. So this must be equal to each other. Then what we have is the amount that was charged must equal to the amount that was discharged. Okay, they must be equal. So we can combine these two equations, and we get a relationship between the output voltage and the source voltage in terms of T on and T off. Okay, so if you combine these two equations, what happens is the L will cancel out, and we get as Vt equals to Vs 1 plus T on over T off. We got this equation as a relationship between the, right, this is a relationship between the input voltage versus output voltage. Okay, any questions about this calculation? So this is the key equation we want to know. This, right, depends on the ratio of T on and T off. But for our very simple calculations, it does not depend on things like, the value of the inductance of L. It does not depend on the diode or the capacitor. All right, so if no question, then let's think of, then what does the capacitor and the diode do? Right, why do I draw this capacitor and diode? When you build a circuit, you do need a capacitor and a diode. But why? What's the point of these? Right, during all these equations, they never showed up. So what? So what does the capacitor do? Why do I need a capacitor in this circuit?
Assuming it discharges when the switch is closed.
You really, okay. So what, right? So I think we're hinting at this as this will reduce the voltage ripples across the load, right? You want to keep the output load fairly constant, right? So here what we're showing is we're computing the average voltage, but you also want the voltage to be fairly consistent. You don't want it to change a lot. So this capacitor try to hold the voltage constant at the output. And what does the diode do?
Quick question. What does
Yeah,
the
go ahead.
ripple mean?
Oh, what does ripple mean? So if you look at Vt as a function of time, it's not exactly a constant line. It's sort of something that goes up like this, right? It goes a little bit up and down. So ripple means how big the variation is around the mean. So you want this ripple to be small. Okay. And for diodes, right? So yeah, so for diodes, the chat is correct. So Dario says is correct. You don't want the backflow from the capacitor, right? Diode stops the capacitor from basically discharging through the switch, through when the switch is closed. So this stops capacitor from discharging when the switch is closed, right? So this is what we want. We want, small ripple. We want, diode prevents backflow. Okay. All right. Okay. So here, based on these, our assumptions will be the following. So make this assumptions. Right. So our assumptions will be that we assume capacitor is large enough. So the RMS voltage will be equal to the average voltage, will be equal to Vs1 plus T on over T off. Right, so we'll assume that we don't want to talk about RMS. Right, so we still want to talk about RMS, but then the computation for RMS gets to be very complicated if you want to take into the ripples into account. So here we're going to assume the capacitor is very large. So the ripples are very small through the voltage. And then the voltage and current where the RMS values are roughly equal to the average values. Right, we'll assume this. Okay, this is the assumption we'll make. And you can make this assumption when the capacitor is relatively large. Questions for this? Okay, so this is our boost converter, right? This is our boost converter. Then if you talk about power, then power is pretty simple to compute in this case. Power in is the input voltage times the input current. Power out is the output voltage times the output current. And then of course, power is conserved in this circuit, right? We're gonna assume that the inductor, capacitor, and the switch does not dissipate power. The diode does not dissipate power, so power is conserved from input to output. Okay, so now let's do an example question about boost converter. The boost converter is a lot more interesting. We'll come to the questions we can ask. But for buck, really is, we don't have any inductor capacitor, so buck, not much we can say about it. But boost is more interesting. Right? We can ask more questions. So let's look at a question. Let's say we have a boost converter that steps up from 20 to 50 volts. The switching frequency is 5 kilohertz. The load resistance is 10 ohms. When you compute the average current of the load, power delivered by the source, average current delivered of the source, and we want to compute how large the inductor should be to limit the current ripple. Okay, so take a closer look at the current ripples. So let's do the first two parts. Right? So let's do the first part. What is the average current of the load? And the first part is really sort of, these calculations are fairly simple. So what is the current in this case? So if you know the voltage, then what's the current? If you know the output is 50 volts, so you know the resistance 10 ohms, what's the current?
V over R.
V over R, right? So this, right, for this kind of converters, the voltage and current calculations are generally not very hard. Right, so here I have V over R, 50 over 10, this is 5x. Okay, so the current is really easy to compute. How about the power delivered by the source? What is the power delivered by the source?
Is it still V squared over R?
There's still V squared over R, or V times T, right? Or V times I. Because power divided by the source is equal to the power consumed by the load. Again, you cannot lose power inside the converter. So how much power comes out needs to be the power that came in. So this can be VT squared over R, or VT times IT. This is 250 watts. Okay. Then the current, right, at the source, this is just power. It doesn't matter, right? So it's only one power value, power over voltage at the source, 250 divided by 20 volts. So this is 12.5. So a converter that steps up the voltage, then the current needs to go down, right? Since power is conserved. So the side that has a higher voltage has smaller current. The side has the lower voltage has larger current for all this calculations. All right, so now let's look at let's look at what the last question means, right? What does it mean for the current ripple? Well, current ripple is the following, is basically how much the current goes up and down in your inside your inductor. So current ripple means if we draw this out, so this is the current in the inductor. And this is called delta I on, delta I on. This is the current ripple. This is how much up and down the current actually moves in your inductor. So we want to find L that makes this small, right? The larger the inductor, the smaller the current ripple. Right? The larger inductor, the sort of the less current you put into it, the less current you put into it. So we want to have a large enough inductor to make the current ripple small. Right? We want to compute as we know that Vs is equal to L delta I on T up. Right? So what we have is so this is the computation we want to do, right? So we need to figure out basically how right, we want to figure out how large L needs to be to keep ion small. Okay. So here is we know Vs, we know delta ion because we are given the value we want to be keep at 100 milliamps. So to solve this, to find out this equation, as we need to find T up, right? We need to find how long this switch is up. So to find out the switch is on, what we have is we have Vt equal to Vs, 1 plus T on over T off. Right? And we know the switching frequency. Right? So we know the switching frequency. We know the frequency is 5 kilohertz. So we know tau is 1 over f is 0.2 milliseconds. And we also know T on plus T off equal to 0.2, equals to tau. Okay, we know this equals to tau. Right? So from this, we can substitute this equation into this equation and solve for the value of TR. And we can solve for this value of TR. So here solving, this is just a linear equation. We solve T on, we get T on equals to 0.12 milliseconds. Then since we know T on and we know L delta I on divided by T on equal to Vs, or L times 100 milliamps divided by 0.12 milliseconds equals to 20 volts. We have L that is 24 millihenries. And so this is the way we size the inductor. Right? So even though the inductor does not impact the average voltage you get, it does impact how big the variations are, the current variations are. So you want the large enough. You want the large enough inductor to make sure the current ripple is small. Any questions about this calculation?
So do you kind of do a similar thing to figure out the size of the capacitor to get rid of the voltage ripple?
Right, so the capacitor is harder to size. So here we're going to assume the capacitor is large enough, but you're right. In practice, you would do this calculation as well for the capacitor. Yes, but just that's a more difficult calculation. So here we're going to only look at the current setting.
Are we also assuming that the voltage across the inductor doesn't go to 0?
Right, so we're going to assume the inductor is large enough that we don't saturate it. So we're going to stay far away from when we're going to saturate the inductor. So linear behavior and the voltage is, so the voltage, yeah, so we're going to assume that you don't have reverse current flow. Again, the capacitor is large enough. And we're going to stay far away from the regime where you saturate your inductors. Okay, so these are good questions. These are very practical things you need to consider when designing this kind of converters. Right, so here we're presenting sort of simplistic viewpoint of just worrying about the average and the current ripple. But in practice, you do have to sort of care more about a lot of other things. Okay, any other questions? Okay, so if not, let's stop here today, right? So we'll have a new homework coming out tonight or tomorrow morning, and we'll cover power electronics. And we're close to the end of power electronics. So next class lecture takes about half an hour to finish the rest. Right? So then we'll go into more larger system considerations or generation and demand. But we'll finish power electronics next Monday. All right, so no questions. I'll see you on Monday. Reminder, homework is due tomorrow night.
I had a question about the homework if you got a second.
Yeah, sure, go for it.
So